My name is Xiaoyu from the University of Illinois at Urbana-Champaign to talk about our recent work by Professor Mehr and myself. The title of the work is Learning to Influence Vehicles Routing in Mixed Autonomy Networks by Dynamically Controlling the Headway of Autonomous Cars. As anticipated by many, road networks will soon be shared between human-driven and autonomous cars, and they will operate under a so-called mixed vehicle autonomy. While the number of vehicles running on the road is certainly going to increase, the problem of the traffic congestion will continue to bother everyone in the future. And this is partially the result of our selfish nature as human beings, always trying to arrive from one place to another as soon as possible. But unlike human-driven cars, which cannot be externally controlled, we can assume a level of control over autonomous vehicles, which provides us with an additional control input to affect traffic networks. In this work, we take a different approach and propose that we can actually dynamically control the headway of autonomous cars on different road links to increase mobility in mixed autonomy networks. In fact, the headway of autonomous vehicles can be leveraged as an infrastructure control strategy to dynamically regulate road capacities, similar to variable speed limits, which regulate the maximum speed of vehicles on the road segment. A control policy can regulate the headway of autonomous cars along each road segment. Here is a fundamental diagram of the density, which is on the horizontal axis, and the flow on the road link on the vertical axis. The maximum flow or the capacity is achieved at those critical density denoted at tilde n, and which is affected by the fraction of autonomous vehicles of all vehicles, which is denoted as alpha in the plot. Generally speaking, autonomous cars will increase road capacity. With such insight, we hope to set up a control policy to regulate the headway of autonomous vehicles on the traffic dynamical system from the capacities to the flow and eventually the road choices of vehicles in the traffic network. In this traffic model, there is this important piece of choice dynamics. The latency E, which is the time vehicles are presumed to spend on road links, will get affected by the flow on the link. And in the equations of this choice dynamics, the latency on the link is somewhat inversely proportional to the flow that will try to go through the same link at the next time step, since vehicles will likely try to avoid the paths that cost more time. Here is this important factor mu indicating the rationality of vehicles. Usually, the larger the mu, the more effective of the latencies on those choice dynamics. Due to a high nonlinearity nature of the system, it is very difficult to use some traditional control methods to dynamically assign headways to different links. Therefore, we propose to use reinforcement learning on this particular problem. The state space of the RL agent is the densities of vehicles on each link. And the action space is, of course, the headway assigned to each specific link at the time step. We designed the reward function to be the negative of total travel time, which is basically that we are trying to reduce sum of densities on all links across the time horizon we consider. For the experimental traffic networks, we study the classic brace network and also an extended network with a brace network embedded in it. The consideration behind this is that if the policy brainlessly trying to increase the capacity of links, it can influence vehicles' road choices in unexpected ways similar to the well-known braces paradox, such that the network congestion might even increase. The policy on dynamically regulated headways learned by the IL agent, in fact, did a decent job. Compared to the baseline in which we try to keep the headway of autonomous vehicles constant at the headway maintained by human-driven vehicles, our agent achieved 4% of improvement with the free flow initial condition and the 13% of improvement with the congested initial condition on the classic brace network, and similarly around 3% and 12% on the extended network. In the next slide, we include the dynamic heat maps of different strategies, in which the red indicates a larger density on the link and the green refers to a less crowded link. With no headway control, the vehicles will eventually block both passes of the network, while with the policy learned by the RL agent, at least one of those passes will be kept at free flow for more vehicles to exit the network, thus reduce the total travel time. In conclusion, we examine the problem of influencing vehicle road choices to maximize mobility in mixed autonomy traffic networks. Our insight into this problem is that mobility can be increased in mixed autonomy networks by dynamically controlling the headway of autonomous vehicles. As a future work, we are looking forward to extending our current method to a multi-agent reinforcement learning method for a larger scale network. That's all for my presentation. Thank you very much.